Why do power lines carry 240,000 volts? And how do we safely reduce that to only 240 volts when it comes to your house? This is what transformers do. They scale voltage, they protect our power grids. So first, what does a transformer do? A transformer doesn't generate energy. It reshapes it. It takes an alternating voltage on one side and it steps it up or down on the other side using two coils. Let me draw a diagram for you. Imagine this is some iron, and usually there's two coils in a transformer. So this is the primary one, it wraps around like this, and this is the input voltage with an N amount of turns. Next, you have the secondary coil, like this. This is the output voltage with an N amount of turns. This is where your voltage comes in, this is where it comes out. But you see, they're not linked by wires. They're linked by a changing magnetic field. And how this works is that since each coil is wrapping around the same iron core, the changing magnetic flux inside of the core induces voltage inside both coils. This is Faraday's law again. I'll show you with math. The output voltage is equal to the number of loops inside of your secondary coil times the change in magnetic flux divided by the time interval. This is Faraday's law. And your input voltage is equal to the same thing. This is on the free cheat sheet in the description, and we can go ahead one step further and divide these two. And what you find is that Vs, our output, divided by Vp, our input, is equal to the number of loops inside the output coil divided by the number of loops for our primary coil. What this tells us is if there's more turns, there's a higher voltage. If there's fewer turns, there's a lower voltage. They're tied. And this formula is also on the formula sheet in the description. So let's go through an example problem. Say a transformer supplies 9 volts at 0.5 amps of current to a phone charger. The secondary coil has 45 turns. Let's solve for 3 things. First, how many turns does the primary coil have to have if the input voltage is 120? 2, what current flows through our primary coil? 3, what is the power that's transferred? Let's go step by step. The GG. First, remember our transformer equation, which is this. And we're going to use it to find NP, which is the primary coil amount of loops. Rearrange for NP, you get NP equals NSVP over VS. The number of spins inside of our secondary coil is 45. The voltage coming through our primary coil is 120. And the voltage on our secondary coil is 9, giving us 600 loops for our coil. Let's keep that number in mind and solve the second problem, which is current. And the thing is, these two are actually connected because to find current, we can use power. We're going to solve for both of these at once. So the current flowing through the primary coil, if you remember power conservation, power is equal to VSIS. VS, the voltage through the secondary coil, is 9, and the current 0.5. This means power is 4.5 watts. And there we find power. But now with power, we're able to find current flowing through the primary coil. Because the current that flows through the primary coil is equal to power over the voltage in the primary coil, which is simply this power equation but rearranged to isolate current. This is 4.5, which is the power in our transformer, over the voltage coming through, 120, giving us 0.0375 amps. That's problem solved. Now let me teach you about the difference between step-up transformers versus step-down. So if the number of loops in the secondary coil is bigger than the number of loops in our primary coil, then it's a step-up transformer, which means it increases voltage and reduces the current. And the other way around, the secondary coil having less loops than the primary one is a step-down transformer. Why does this matter? Because power is equal to current times voltage. For a fixed power, this means if you increase the voltage, to keep the equation balanced, current must decrease. More voltage, less current. Lower current means there's less heat loss in your wires. So imagine some big industrial power lines. Let's say our power plant is over here making power. There's smoke because it's a power plant. We have a big step-up transformer system going on here. Wires come in and it goes up to the power lines. I'll just represent with rectangles. And these are super high voltage. And what happens after this, it comes down to a step-down transformer or a substation. And it comes down, it goes to the smaller like wooden power lines that you might see. Then there's another step-down transformer before it enters your house. So if you have 12,000 volts coming in from the power plant, the step-up transformer will increase it to 240,000 volts. And it travels across here, and then the step-down transformer will make the voltage 7,200, for example. And then the final one, right before it reaches your house, will reduce it to 240. This is the important role of transformers in transmission of electricity. And since electricity must be transmitted over long distances, since power plants are usually quite far from most people's houses, or even from buildings in general, there's always some power loss in the transmission lines. And this loss is minimized if the power is transmitted at a higher voltage, aka a low current, using transformers. So transformers let you scale voltage up and down, using only changing magnetic fields. It's how you power your city, it's how you charge a phone, and these are the most important equations for transformers, which are also on the free cheat sheet. And power is conserved, with high voltage transmission being efficient, low loss delivery.